As Piranza said, I'm Eva, hi, and in my group there are also Robert, Christopher, and Timo, and we are working on the fire forecasting project. To give you a little bit of context about our project, the context is in fire emission estimation, and there are, let me change the slide. Yeah. There are satellites which measure fire emissions or measure fires. For example, they measure fire radiative power, FRP. We will use this term in the future. Like, for example, the Aqua or the Terra satellite. And these satellite measurements of fire, they are then used by different models, which use the satellite measurements to estimate actually the fire emissions, for example, of CO2 or CO. One of these models is, for example, the global fire assimilation system, which then used, like I said, the FRP for its fire emission estimates. And here on the lower left, you can see tracks or the positions of these two satellites, and also the tracks they go around the Earth. And both of them, they are sun-synchronous satellites. And what you can see as a result of that is that they do not pass each point on the Earth that often. That means for each position on the Earth, they pass the maximum 2 to 3 times per day. And furthermore, another problem is that these satellites cannot measure fire when it's cloudy. So when there are clouds, they do not see anything. And both these discrete satellite overpass time and also the cloud coverage, that leads to the fact that for a certain position, there are large observation gaps. And with our project, we try to develop machine learning approaches to fill these gaps for one position so that you can have a whole time series for one location on Earth about the fire emissions. So the goal of our project, or the current goal, is to estimate 24 hours of fire emissions based on the 24 hours before the fire measurements we have there and other meteorological parameters. And what we want to produce, or our final goal, is to have a framework where we can apply different machine learning models to test which one is the best. And we then want to have an operational forecast, meaning that we do not only estimate the next 24 hours, but day by day, we can create a longer time series of fire forecast. What you can see here on the lower part, there's a sketch of the modeling parts we want to develop, or the programming parts we want to develop. So we first now had to deal with the data set and created a data set for our machine learning models. So we developed that, but we also implemented the machine learning models themselves and the training and test framework. Furthermore, what we needed was a data loader. And with all this together, we then could produce a forecast. And in the following 2 slides, I want to present you our data sets and some characteristics of our data set. And afterwards, Robert will continue and present you our first results. As you can see here on this map, in the middle of my slide, we focused on the Northern Hemisphere and satellite measurements on the Northern Hemisphere. And what we did now to create our data set for our machine learning models is that we selected different pixels, so spatial pixels, but also in time, when there was a fire within 1 day. And on the following day, we still had satellite measurements. So we selected each of these 0.5 degree grid cells and stacked them together. And this is somehow shown here below. So what we did is to not only select the fire pixel itself, but also the pixels surrounding it. And for the first 24 hours where was a fire, and the next 24 hours where we had at least 1 measurement. So we then get a 3 times 3 times 48 data set. And as we have 2 satellites, 2 times of it, And this then resulted in 10,000 or roughly 10,000 periods we selected for our training data. And we furthermore did is to shift all these 24-hour sequences by 1 hour, so that we had 24 times these 10,000 periods. We tried to somehow characterize these data set, and this is now shown here. I want to point out some special things. If you look at the upper left plot, you can see a histogram of the number of the selected pixels or the pixels in our data set, depending on the fire strength they show. And as you can see, the majority of the pixels do only have a small fire radiative power. So there are a lot of small pixels, with small fires in our data set. If you now focus on the top right plot, you can see a histogram of how many fire measurements or how many hours of fire measurements do we have within the 48 hours. And there you can see that mainly we just have 1, 2, 3, maybe 4 measurements within this 48 hours of fire for the most of the pixels. And furthermore, what you can also see when you look at the third plot, so the lower left plot, there is shown how many fire hours are next to each other. So how long are the periods we have fire measurements 1 hour after the other without interruption. And there you can see that mainly we just have 1 or maybe 2 hours of subsequent fire measurements. So normally there's a fire measurement, a gap, and at some point later there's again a fire measurement, which makes it more difficult to have kind of a time series or a time development of the fire. And finally, what we also looked in before implementing the models was at our meteorological data sets, so which parameters could be interesting. And we had a look at the correlations, which you now see on the lower right. And as you can see, first of all, on the upper side, that vegetation plays a role, so over here. But what you can also see is that the boundary layer height, which somehow parameter which reflects whether we have a high pressure or low pressure system, is also important. And as expected, the temperature and also humidity, and a bit also the precipitation and velocity. And with this, we then selected which data we want to use in our machine learning model. And with this, I'm handing over to Robert.
Yes, as Eva explained, next slide, please. How our dataset looks like. We tried some algorithms on the dataset. The main challenge is that the input data is sparse because we have not complete coverage by the satellites. But we wanted to test the 5 algorithms on the data without regarding the sparse data at first, just to see the results, if it already works. And so what we did is we selected 9 variables from the data set for the last 24 hours and 24 hours in the future as features, plus the FRP from the last 24 hours and the fraction of area observed, so the satellite coverage. And what we predicted, the target was the fire rated power 24 hours in the future. The models were trained on the complete data set. So if there was no satellite coverage, the models should learn to output 0. But the evaluation was only where there was actually coverage from a satellite. The first model here is just the assumption that there's persistence. So this means that for the next 24 hours, it's just the mean value of fires in the previous 24 hours. And we see here from the 5 models, this is the most simple one, and then get more complex down to multilayer perceptron, which is a kind of neural network. And we see that in this case, the root mean squared error of the persistence is actually the best, and also the correlation. So this motivates for us to definitely implement a way to handle the sparse data. But this was just the first step, and mainly look at what time series do the models actually produce. So first we look at the ridge regression. And we can see here on the y-axis for all 5 plots, so it's 5 different feature and target sets. On the y-axis, the radiative power of a fire. And the left side in blue, we have the previous fire. And on the right side in orange, the target, in orange, and in green, the prediction. You can see here that the background is shaded in gray, where we have no observations of the satellite. So it's 0 in our data set. And we can see that at the right areas in the plot, on the left side, we have some signal. And on the left side and on the right side as well. And we see that the ridge regression, the linear model, is not able to predict any of this evolution because it outputs 0 for every step. But we can still look at the parameters of the ridge regression, which is a linear model. And what we see here on the y-axis are the 9 features that were used for the model. And on the x-axis, it's the time for the output prediction. So 0 is the first hour after first hour of the output to the 24th hour. And we see here in yellow, it's a scale of the importance of the features in the model. And we see that the mean sea level pressure, next please, has the highest importance, most important feature, which seems reasonable because changes because it symbolizes a low or high pressure system. So it's an important indicator for the weather. And there's another interesting thing in this plot, and there's a gap in the 14 hours to 20th hour, and we don't know yet why there's this gap. And it might be something to do with the structure of our data set and the timing of the satellite measurements, if they come one after another. So that is something we want to investigate in the future. Next, please. And we can also look at the most complex model, this multi-layer perceptron. And here we can see that the model actually outputs for areas where we have a signal, actually outputs radiative power. So this is a good indicator because we have not really performed hyperparameter tuning for the models. And we also have not included the possibility to handle sparse data, but still the model already displays signs that it can handle the data. So we're pretty optimistic that in the future, if we implement the sparse data handling by creating custom learning algorithms, that we will be able to beat the assumption of persistence for the fires.
Okay, and with this, we're coming to the end of our talk and wanted to give a short outlook what we planned to do right now. So I think there are 3 main points. First of all, like you might have seen on the correlation plot, precipitation right now doesn't seem to play such an important role. And we expect that this might change if we do not look only at certain time steps, but rather also the time development, so the time derivative, because actually a fire stops when it rains. And we also want to identify nonlinear correlations between the parameters. And like Robert already mentioned, we want to improve all our learning algorithms and also include hyperparameter tuning. And finally, what we also want to do, and what is shown on the right side in terms of satellite measurements, we have this nice time series, for example, over a month. And we do want to expand, therefore, our time series not to only have 2 days, but rather, for example, look at a month, like shown here on the right side. With this, thank you very much for your attention, and please just write your questions like we said in the chat. Thanks.
Thank you very much, team. Impressive results, so well done. We have a question for you. So I read it loudly for you. Why do you think the correlation with surface pressure was low? Do you want me to repeat?
Maybe once again.
Yes, you can also read it in the Q&A. Why do you think the correlation with surface pressure was low?
Okay, maybe this addresses, because like Robert said in his model, it showed that the mean surface pressure was correlated. We don't know exactly. I mean, that will be also part of the further analysis, I think, why certain parameters show correlations and certain don't, like I mentioned, for example, for the precipitation, but then also for the surface pressure. Yes.
Thank you very much.